Tonight, we're going to look at the fastest journey physics permits and at the price it quietly attaches to every kilometer per second above a certain line. The space between the stars is the emptiest volume any human instrument has ever measured. In the corridor our solar system is currently drifting through, there is roughly 1/10 of a hydrogen atom in every cubic centimeter, not 1/10 of a gram. 1/10 of a single atom, averaged across a volume about the size of a sugar cube. The best vacuum chambers ever built on Earth are, by comparison, crowded rooms. And that emptiness holds. It holds at walking pace. It holds at the speed of a rifle bullet. It holds at the 11 kilometers per second that lifted Voyager 1 out of the solar system. And it holds at every speed any object built by human hands has ever traveled. The medium simply does not notice you, and you do not notice the medium. Then there is a line. It is not a sharp line, and different engineers place it in slightly different places, but it sits somewhere near 1/10 of the speed of light. Below it, interstellar space behaves like emptiness. Above it, the same 1/10 of an atom per cubic centimeter stops behaving like emptiness and starts behaving like a beam. The hydrogen does not change. Your relationship to it changes. Every atom in your path arrives carrying kinetic energy you supplied, aimed at the front of your ship at a rate that rises far faster than your speed does. And here's the part that does not reverse. You cannot steer around it because it is not in one place. You cannot outrun it because running is what creates it. You cannot switch it off because the only way to switch it off is to slow down, and slowing down is the single most expensive thing a relativistic ship can attempt. The medium is in front of you for the entire voyage, and the faster you go to shorten the voyage, the harder the medium hits. But could a crew simply build a thicker wall and accept the bill? By the end of tonight, you're going to understand exactly what the interstellar medium becomes at relativistic speed, why the shield that stops it creates a second and worse problem inside itself, and why the cruise speed that looks most attractive on paper is the one the arithmetic punishes hardest. Before we get started, if you love exploring the physics of deep space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing to establish is what near light speed actually means, because the phrase covers an enormous range of behavior, and almost all of the interesting trouble happens in one narrow band of it. Light moves at 299,792 kilometers per second. Physicists write that as c, and they describe every other speed as a fraction of it. A commercial airliner cruises at about 0.000000. The International Space Station orbits at roughly 0.000026. Voyager 1, the fastest departing object humanity has ever released, is leaving the solar system at about 17 kilometers per second, which is 0.000057 K. Parker Solar Probe, at its closest approach to the Sun, briefly touched about 0.00064 and became the fastest human-made object in history. Every one of those numbers is small enough that relativity is a rounding error. The clocks aboard those spacecraft do drift, and engineers do correct for it. but the correction is measured in microseconds per year. Nothing about the physics of flight changes. A spacecraft at 0.0006 degree is, for every practical purpose, a spacecraft moving through nothing. The band this episode is about begins around 0.1 kS and runs upward. At a tenth of light speed, a ship covers 30,000 kilometers every second. It crosses the distance from the Earth to the Moon in 13 seconds. It reaches Alpha Centauri at 4.37 light years in a little under 44 years. That is the first speed at which an interstellar mission becomes a thing a human institution could conceivably plan around, rather than a thing that outlives the civilization that launched it. It is also the first speed at which the medium starts to matter. This is not a coincidence, and it is not a design flaw in any particular ship. It is a consequence of how kinetic energy behaves. The Lorentz factor, written as the Greek letter gamma, is the number that measures how far a given speed has departed from ordinary Newtonian behavior. At rest, gamma is exactly 1. At a tenth of light speed, gamma is 1.005. At 2/10, it is 1.021. At half of light speed, gamma is 1.155. At 8/10, 1.667. At 0.99 C, gamma has climbed to 7.089. And at 0.999 K, it reaches 22.37. Notice the shape of that progression. Gamma barely moves through the first half of the speed range and then climbs without limit as you approach the last few percent. That shape is the whole story of this episode in a single sequence of numbers. Every benefit of relativistic travel and every penalty of relativistic travel is governed by gamma. And gamma is a curve that punishes ambition specifically at the top. The ladder of speeds, then, looks like this. Below 0.01 K, you have an ordinary spacecraft with an extraordinary engine. Between 0.01 K and 0.1 K, you have a genuine interstellar probe with a mission duration measured in centuries. Between 0.1 K and 0.5 K, you have a ship, and you have a hazard environment no vehicle has ever operated in. Above 0.5 K, you have a machine whose principal engineering problem is no longer propulsion at all. The interesting thing about that last sentence is how few people expect it. The popular version of interstellar travel treats the engine as the hard part and everything else as detail. The arithmetic says otherwise. The reason anyone accepts that hazard environment at all is a single genuine gift, and it deserves to be stated precisely because it is usually described in a way that makes it sound like more than it is. Time dilation is real. It is not a mathematical convenience, not an illusion of measurement, and not a philosophical position. It has been measured directly, repeatedly, and to extraordinary precision. Muons created in the upper atmosphere reach the ground in numbers that make no sense unless their internal clocks are running slow relative to ours. Atomic clocks flown on aircraft return with measurably different readings from their stationary twins. Every satellite navigation system on Earth applies relativistic corrections continuously and would accumulate navigation errors of kilometers per day without them. Here is what dilation does for a starship. If a ship travels at a speed where gamma equals 10, Then the crew ages 1 year for every 10 years that pass on Earth. Their coffee cools at the normal rate. Their heartbeats sound normal to them. Nothing aboard feels slow, but the distance between the ship and its destination, measured in the ship's own frame, has contracted by that same factor of 10. A 10 light year journey becomes a 1 light year journey as far as the ship is concerned, and the crew crosses it in a little over a year of live time. That is the offer, and it is a genuinely remarkable offer. It means interstellar distance is not, in principle, an absolute barrier to a human lifetime. A sufficiently fast ship can cross the galaxy within the biological span of the people aboard it. The physics permits this. Nothing in relativity forbids a crew from reaching the far side of the Milky Way in 40 years of personal time. But notice what the offer does not include. It does not include the Earth frame duration. The people who launched the ship still wait the full 10 years, or the full 100,000. Dilation compresses the crew's experience of the trip. It does not compress the trip. From the vantage point of everyone who stayed behind, the voyage takes exactly as long as light would take, plus the time lost to being slower than light. It does not include a discount on energy. This is the misunderstanding that does the most damage in casual discussions of relativistic flight. Because the crew's clock runs slow, it is tempting to imagine the ship is somehow getting the journey at a reduced rate. The opposite is true. The kinetic energy required to reach a given gamma scales with gamma itself. So the very factor that shortens the crew's clock is the factor that inflates the fuel bill. Dilation is not a discount. It is a receipt written in a different currency. And it does not include immunity from the medium. This is the part that will occupy most of tonight. The same length contraction that shortens the corridor also compresses everything in the corridor. The interstellar hydrogen the ship must cross does not thin out because the ship is fast. In the ship's frame, it arrives sooner, closer together, and carrying more energy each. The gift and the penalty are the same effect, viewed from two sides. To make the gift concrete, it helps to run the arithmetic of a specific voyage rather than to speak in generalities. The standard version of this calculation assumes a ship under constant acceleration of 1g, which is 9.81 meters per second squared, Earth's surface gravity, and therefore the acceleration of the human crew could tolerate indefinitely without physiological decline. A ship that accelerates at 1g and never stops accumulates speed quickly at first, and then approaches light speed asymptotically, never reaching it. Here is what the ship's own clock records. After 1 year of ship time, the vessel is traveling at 0.775 K. Its gamma is 1.58. Back on Earth, 1 year and 2.2 months have passed, and the ship has covered 0.56 light years. After 2 years of ship time, the speed is 0.968 C, and gamma has reached 4.01. Earth has aged 3 years and 9 months. The ship has crossed 2.91 light years, which is already most of the way to Alpha Centauri at 4.37 light years. After 3 years of ship time, the ship is at 0.996, gamma is 11.1, Earth has aged 10 years and 8 months, and the distance covered is 9.78 light years. After 5 years of ship time, gamma stands at 87.4. Earth has aged 84.6 years, most of a human lifetime, and the ship has covered 83.6 light years. There is the shape of the bargain, laid out in 5 lines. Ship time grows arithmetically. Earth time and distance grow exponentially. A crew that is willing to spend 5 years of their lives can cross more than 80 light years, and that is a genuinely extraordinary statement about the structure of space-time. But every one of those lines carries a second column that the popular version omits. At 1 year of ship time and gamma 1.58, the proton density in the ship's frame has already risen by 58%, and each proton arrives with about 545 million electron volts of kinetic energy. That is comparable to the beam energy of a mid-sized proton therapy accelerator, the kind used in hospitals to destroy tumors, except the beam is continuous. It covers the entire forward face of the ship, and it cannot be turned off. At 2 years and gamma 4.01, each incoming proton carries about 2.8 billion electron volts. That is within an order of magnitude of the beam energy at the alternating gradient synchrotron at Brookhaven, a facility that occupies a substantial fraction of a national laboratory and is surrounded by concrete measured in meters. At 5 years and gamma 87.4, each proton arrives with about 81 billion electron volts, and the flux has risen by a factor of 87 on top of the velocity increase. You are inside a machine that is generating its own particle accelerator by the simple act of moving forward, and the beam intensity is set by your speed, which is the one parameter the mission profile is least willing to reduce. The second cost is the one people usually do expect, though rarely at the correct magnitude. Getting to relativistic speed requires energy, and the amount is difficult to hold in the mind. Kinetic energy at relativistic speed is not the familiar 1/2 mv squared from a physics classroom. That formula is an approximation that only works when the speed is small compared to light. The correct expression is gamma minus 1 multiplied by the mass multiplied by the speed of light squared. The c squared is what makes the numbers behave the way they do. Consider a ship with a mass of 1,000 tons. That is a modest figure for something carrying a crew across interstellar distance, roughly 2.5 times the mass of the International Space Station, and about 1/5 of the dry mass of a Saturn V at launch. It is not a generation ship. It is not a habitat. It is a vessel. To bring 1,000 tons to 1/10 of light speed requires 4.53 times 10 to the 20th joules. Humanity's total primary energy consumption across every power station, every engine, every furnace, and every fire is roughly 6.3 times 10 to the 20th joules per year. So the kinetic energy of a single 1,000-ton hull at 0.1 Quan is about 72% of everything the species burns in a year. And that figure is the energy that ends up in the ship. It assumes perfect conversion, perfect coupling, and zero waste, which no propulsion system has ever achieved or ever will. Raise the target speed to 2/10 of light speed, and the requirement becomes 1.85 times 10 to the 21st joules, about 3 years of total human energy use. At half of light speed, 1.39 times 10 to the 22nd joules, which is 22 years of everything. At 0.9 C, 1.16 times 10 to the 23rd joules, which is 185 years of total human energy production delivered into a single 1,000-ton object. These numbers are not arguments that relativistic travel is impossible. A civilization with substantially more energy available than ours could pay them. The sun radiates about 3.8 times 10 to the 26 watts, so the entire energy budget of a 0.9 K voyage represents roughly 300 seconds of total solar output. Captured at any meaningful efficiency, the resource exists. The point is different, and it is a point about shape rather than scale. The energy cost rises with gamma. Every other penalty in this episode also rises with gamma, and several of them rise faster. There is no speed at which the bill stops growing, and no speed at which the growth slows down. You are climbing a curve whose gradient increases forever, and the destination you are trying to reach sooner does not move closer as you climb. That asymmetry is what makes the trade harder than it first appears. It is not that fast travel is expensive. It is that fast travel is expensive in a way that compounds against itself. Energy, though, is not the binding constraint. A civilization can imagine having more energy. What it cannot imagine away is the rocket equation, which does not care how much energy you have, only how fast you can throw things backward. The relativistic rocket equation is best understood through a quantity called rapidity. Rapidity is the inverse hyperbolic tangent of your speed as a fraction of light speed, and its useful property is that it adds. If you make one burn that changes your rapidity by a certain amount, and then a second burn that changes it by the same amount again, your total rapidity is the sum. Velocity does not behave this way at relativistic speed. You cannot add 0.6 and 0.6 k and get 1.2 k. But rapidity does, and that makes it the natural currency of relativistic propulsion. At a tenth of light speed, rapidity is 0.100. At 2/10, 0.203. At half, 0.549. At 0.9 C, 1.472. At 0.99 C, 2.646. The mass ratio a rocket needs is the exponential of the rapidity divided by the exhaust velocity, expressed in the same units. The exhaust velocity is therefore not one factor among many. It sits in the denominator of an exponent, which is the most punishing position a number can occupy in engineering. Take a fusion drive. An optimistic exhaust velocity for a fusion pulse system is about 0.05 C, 5% of light speed, which is already a stretch beyond anything demonstrated. To reach a tenth of light speed one way, that drive needs a mass ratio of 7.4. Every ton arriving requires 7.4 tons at departure. That is demanding, but it is comparable to a large chemical launch vehicle, and it is clearly within the realm of engineering. To reach 2/10 of light speed one way, the same drive needs a mass ratio of 57.7. To reach half of light speed one way, it needs a mass ratio of 59,050. Read those three numbers again in sequence. Doubling the target speed from 0.1 crit to 0.2 multiplied the fuel requirement by 8. Doubling again to 0.4 crit would multiply it by roughly 60 more. Reaching 0.5 crit requires a departure mass 59,000 times the arrival mass, which means the 1,000-ton ship must leave with 59 million tons of fusion fuel. comparable to the total mass of every ship in the world's merchant fleet, assembled in orbit and then thrown away in a single voyage. Doubling the exhaust velocity helps enormously because it halves the exponent. A drive with exhaust at 0.1 crace reaches half of light speed on a mass ratio of 243 instead of 59,050. But exhaust velocity is set by physics, not by ambition. Fusion releases about 0.4% of rest mass as energy, which caps the achievable exhaust velocity in the region of a few percent of a key, even with perfect conversion and perfect collimation. There is exactly one propellant that escapes this trap, and it has problems of its own. Antimatter deserves its own consideration because it is the only propellant that makes the rocket equation cooperate rather than resist. When matter and antimatter annihilate, the entire rest mass of both participants converts to energy. Not 0.4%, as in fusion, not 0.000000005%, as in the best chemical reactions. All of it. That is the theoretical maximum any propellant can offer, and it means an antimatter drive can in principle produce exhaust at a substantial fraction of light speed. A perfect photon rocket, one whose exhaust is pure light, moving at exactly c, represents the absolute ceiling. Its mass ratio to reach a given speed and then stop again at the far end is 1 plus beta divided by 1 minus beta, where beta is the speed as a fraction of c. At 2/10 of light speed, that ratio is 1.5. At half of light speed, 3. At 8/10, 9. At 0.9 c, 19. At 0.99 key, 199. Those figures are transformative compared with fusion. A ship that needed 59,000 times its own mass in fusion fuel to reach half of light speed one way needs 3 times its own mass in a perfect photon rocket to reach half of light speed and stop. That is the difference between an impossible mission and a merely difficult one. The problem is not the physics. The problem is the supply chain. Antimatter does not occur in usable quantities anywhere we can reach. It must be manufactured, one particle at a time, in accelerators at an energy cost far greater than the energy the antimatter will later release. Current production at facilities such as CERN's antiproton decelerator is measured in nanograms per year, and much of that is consumed in the experiments that produce it. The total quantity of antihydrogen ever assembled and held by human beings is small enough to be counted in individual atoms. A ship of 1,000 tons traveling at half of light speed with a photon drive needs a mass ratio of 3, which means roughly 2,000 tons of propellant, half of which is antimatter. 1,000 tons of antimatter. Against a current global production rate that would need to be improved by something in the region of 20 orders of magnitude. Then there is storage. Antimatter annihilates on contact with anything, which means it cannot touch a container wall ever for the entire duration of the voyage. It must be held in magnetic and electrostatic traps, powered continuously with no permitted failure. 1,000 tons of antimatter suspended in a magnetic bottle for a decade aboard a vessel that is simultaneously being bombarded by relativistic protons is not a fuel tank. It is a condition. And a photon rocket, by definition, converts its propellant into a beam of gamma radiation directed backward at the origin. The exhaust of an ideal antimatter drive is one of the most energetic directed emissions a civilization could produce. Departure is not a neutral act. Antimatter fixes the rocket equation. It does not fix the mission. Assume the propellant problem is unsolvable. The next question is whether you can avoid carrying propellant at all. And here there is a genuinely elegant answer that changes the arithmetic completely. Beamed propulsion leaves the engine at home. Instead of carrying fuel, the spacecraft carries a sail, and the energy is delivered from outside. A laser array in the solar system pushes on the sail, and the sail pushes on the payload. The rocket equation, which punishes you for accelerating your own fuel, simply does not apply because you are not accelerating your own fuel. The mass ratio is 1. Breakthrough Starshot is the most fully developed version of this idea. Its design targets gram-scale spacecraft, a sail a few meters across, and a payload chip weighing about as much as a paperclip, accelerated by a ground-based laser array to about 0.2 quark, reaching Alpha Centauri in roughly 20 years. The acceleration phase lasts minutes, not years, because the sail is so light and the beam is so intense. That is a real proposal with a real engineering program behind it, and it is the reason 0.2 Ka has become the reference speed in the relativistic hazard literature. When you see a paper calculating dust erosion or gas damage at 0.2 of light speed, it is usually calculating it for Starshot. The cost of leaving the engine at home is precise and severe. You lose the ability to stop. A beamed sail can be pushed away from the transmitter. It cannot be pulled back toward it. The laser array in the solar system can accelerate the sail outbound and can do nothing whatsoever about the sail's arrival at the far end. There is no corresponding array at Alpha Centauri, and building one would require getting there first. So a Starshot probe does not visit Alpha Centauri. It passes through the Alpha Centauri system at 0.2 of light speed, which means it crosses the entire habitable zone of the target star in a matter of hours, gathers what data it can in that window, and continues into the dark on the far side, forever. The mission is a flyby measured in hours after a cruise measured in decades. For a gram-scale probe carrying a camera, that may be an acceptable trade. Voyager's Neptune encounter was also a flyby, and it remains one of the most productive days in planetary science. For anything carrying people, it is not a mission at all. A crewed vessel that cannot stop is not exploring the destination. It is sightseeing at a speed that makes sight impossible, and then dying in the interstellar medium beyond. Which brings us to the half of the voyage that almost every popular account leaves out. The deceleration problem is the most consistently underestimated element in interstellar mission design. And the reason is simple. Acceleration is dramatic and deceleration is not. Every mission profile that involves stopping at the destination is really two missions. You must accelerate to cruise speed, and you must decelerate from cruise speed. In a rocket, those are not two equal costs. They are two costs that multiply. Here is why. The rocket equation gives the mass ratio for a single change in rapidity. If you need to accelerate and then decelerate, you need twice the rapidity change, which means the exponent doubles, which means the mass ratio squares. A mission that needed a mass ratio of 58 to reach 2/10 of light speed one way needs a mass ratio of roughly 3,300 to reach it and stop. A mission that needed 59,000 to reach half of light speed one way, about 3.5 billion to reach it and stop. Squaring a large number produces a number that is not merely larger. It produces a number in a different category of feasibility. There is a second effect that compounds the first. The propellant you will burn for deceleration must be carried through the entire acceleration phase and the entire cruise. It is payload, from the engine's point of view, for the whole outbound leg. So you accelerate your braking fuel to cruise speed at full cost, carry it across the interstellar gap, and only then spend it. Every ton of braking propellant costs you the full acceleration mass ratio before it does any work at all. And here's the thing nobody likes to say plainly. Almost every interstellar mission ever designed in detail simply declined to solve this. Project Daedalus, the British Interplanetary Society study, conducted between 1973 and 1978, remains the most thoroughly engineered interstellar vehicle ever put on paper. It was a two-stage inertial confinement fusion ship with a departure mass of about 54,000 tons, designed to reach Barnard's star at a cruise speed near 0.12 degrees Celsius. It carried no deceleration stage. The plan was to release instrument probes ahead of the main vehicle and take data during a flyby lasting a few tens of hours after a 50-year cruise. That was not an oversight. The Daedalus team understood the mass penalty precisely, and they concluded that a braking stage was not affordable within the design. So they designed a mission that did not break. The consequence deserves to be stated without softening. The default interstellar mission, as actually engineered by the people who have engineered them, is a mission that arrives, observes for less than 2 days, and leaves forever. Everything else, orbit insertion, extended study, landing, return, sits behind a mass ratio that squares. There are ways to brake without carrying propellant, and they deserve serious consideration because they represent the only realistic path to a mission that actually stops. The magnetic sail is the leading candidate. The principle is that a large superconducting loop generates a magnetic field which interacts with the ionized component of the interstellar medium. Charged particles streaming past the ship are deflected by the field, and by Newton's third law, the deflection pushes back on the loop. Fly a magnetic sail forward through a plasma and it experiences drag. Drag is free braking. The appeal is obvious. The medium the ship has been fighting for the entire cruise, the same tenth of an atom per cubic centimeter that has been eroding its bow and irradiating its crew, becomes, at the end of the voyage, the thing that slows it down. It is a genuinely elegant reversal. The difficulty is that the numbers are unforgiving in exactly the same way as everything else. Drag force scales with the density of the medium and with the cross-sectional area the magnetic field presents. The density is fixed and extremely low, so the area must be enormous. Magnetic sail proposals typically call for loops tens to hundreds of kilometers in radius, carrying currents that require superconductors operating continuously for decades in a radiation environment that degrades superconductors. Deceleration times are correspondingly long. A magnetic sail large enough to be practical still takes years to decades to shed relativistic speed, which means the braking phase must begin a substantial fraction of a light year before arrival, which means the navigation problem must be solved with extreme precision at a point where the destination is still a point of light. There is a related concept, sometimes called the magnetic ram scoop or the Bussard variant, in which the same field funnels interstellar hydrogen into a fusion reactor. Robert Bussard proposed this in 1960, and it remains one of the most attractive ideas in the field because it appears to solve fuel and braking simultaneously. Subsequent analysis has been consistently unkind to it. The drag produced by scooping generally exceeds the thrust produced by burning what you scoop, unless the fusion efficiency is extraordinarily high and the scoop is extraordinarily large. The consensus is not that the ram scoop is impossible, but that it works better as a brake than as an engine, which is a real result, but a different one from the one it was proposed for. Photon braking is the third option. Turn the ship around and fire the drive forward. It works, it requires no new physics, and it costs the full squared mass ratio, which returns us to the problem we were trying to escape. None of these are dismissals. Magnetic braking in particular is probably the most promising unsolved problem in interstellar engineering, but all three share a property that will recur throughout tonight. They improve as speed decreases and degrade as speed increases. Every honest solution to a relativistic problem is, in part, an argument for going slower. Now we can turn to the medium itself and to the number that governs everything that follows. In the corridor our solar system currently occupies, interstellar space contains roughly 1/10 of a hydrogen atom per cubic centimeter. That figure requires immediate qualification because it is an average across a region that is not uniform, and the variation matters. Our neighborhood sits inside a structure called the local bubble, a cavity in the interstellar medium, roughly 300 light-years across, carved out by supernovae over the past 10 to 20 million years. The gas inside the local bubble is hot, ionized, and extremely thin, with a density of about 0.05 atoms per cubic centimeter. Within that cavity, the sun is currently passing through a somewhat denser wisp called the local interstellar cloud, sometimes informally called the local fluff, which is warm rather than hot at about 6,700 Kelvin, largely neutral, and denser at roughly 0.1 neutral hydrogen atoms per cubic centimeter. Direct measurement is now possible. When New Horizons crossed beyond the influence of the solar wind's densest regions, its solar wind around Pluto instrument was able to constrain the density of the interstellar hydrogen entering the heliosphere, returning a figure of about 0.127 particles per cubic centimeter. That is roughly 120 hydrogen atoms in a volume the size of a carton of milk. Hold that image because it is the correct one. A carton of milk containing 120 atoms. Whatever intuition the word gas produces, this is not that. The air in the room around you contains about 2.5 times 10 to the 19th molecules per cubic centimeter. Interstellar space at zero point 0.1 atoms per cubic centimeter is thinner than the air you breathe by a factor of 250 billion, and yet the honest version of this number includes its uncertainty. Published estimates of local density range from about 0.03 to about 0.3 atoms per cubic centimeter depending on the sightline, the method, and whether neutral or ionized hydrogen is being counted. A factor of 10 sits inside that range. For emission, a factor of 10 is not a footnote. Every hazard in this episode scales linearly with density. A corridor 10 times denser produces 10 times the radiation dose, 10 times the erosion, and 10 times the drag. And the corridor to any particular star is not the corridor we happen to be sitting in. The local interstellar cloud is roughly 30 light-years across. Alpha Centauri, at 4.37 light-years, is inside it. Barnard's star, at 6 light-years, sits near its edge. Anything beyond about 15 light-years involves flying through material we have characterized only by absorption lines in the light of distant stars. That is the substance the rest of tonight is about. 1/10 of an atom per cubic centimeter, known to within a factor of 10, and completely harmless until the moment you decide to hurry. The transformation from harmless emptiness into a hazard is entirely a matter of reference frames, and it is worth walking through slowly because everything downstream depends on getting it right. Sit still in interstellar space. The hydrogen around you is not still. It has thermal motion, and at 6,700 Kelvin, a hydrogen atom moves at about 11 kilometers per second on average. But that motion is random. Atoms arrive from every direction in equal numbers, each carrying a kinetic energy of a fraction of an electron volt. A hull sitting in that environment experiences a gentle isotropic patter of atoms too weak to register on any instrument designed for a spacecraft. Now move. The moment the ship acquires velocity, the isotropy breaks. In the ship's frame, the hydrogen is no longer a still gas. It is a wind, arriving from directly ahead, at exactly the ship's speed, with almost no spread in direction. Two things then happen simultaneously, and both of them get worse with gamma. The first is flux. The number of atoms striking each square meter of the bow per second is the density multiplied by the speed. At 0.1 key, with a density of 0.1 atoms per cubic centimeter, that is about 3 times 10 to the 12th protons per square meter per second. 3 trillion, every second, on every square meter of forward-facing surface. And length contraction adds a further factor of gamma, because in the ship's frame, the corridor ahead is compressed, and its contents are correspondingly concentrated. The second is energy per particle. This is where the numbers stop being intuitive. A hydrogen atom striking the ship at speed, V carries a kinetic energy in the ship's frame of gamma minus 1 times the proton rest mass times c squared. The proton rest energy is 938.272 million electron volts, and that constant does the heavy lifting. At 1/10 of light speed, each proton arrives with 4.7 million electron volts. That is already comparable to the energy of an alpha particle from radioactive decay, enough to ionize atoms along its path and to damage biological tissue. At 2/10 of light speed, 19.3 million electron volts. At half of light speed, 145 million electron volts. That is inside the range used in clinical proton therapy, where beams of roughly 70 to 250 million electron volts are aimed at tumors precisely because they deposit destructive energy inside human tissue at a controlled depth. At 8/10, 626 million electron volts. At 0.9 degrees Celsius, 1.21 billion. At 0.99 T, 5.71 billion electron volts per proton, which is within a factor of a few of the injection energy at major particle physics facilities. Combine those two effects and the picture is complete. The forward face of a relativistic ship is being struck by trillions of particles per square meter per second, each carrying the energy of a therapeutic or research-grade particle beam continuously for years. The vacuum did not change. Your speed changed, and the medium, which cannot be evaded, is now aimed at you. The formula that governs all of this, gamma minus 1 times mc squared, deserves a moment on its own because its behavior explains why relativistic hazard is not a linear problem. At low speeds, gamma minus 1 is approximately 1/2 beta squared, which recovers the familiar Newtonian kinetic energy. Double the speed, quadruple the energy. That is the intuition everyone carries from everyday experience, and it holds well up to about 1/10 of light speed. Above that, the approximation degrades and then fails entirely. Going from 0.1 K to 0.2 multiplies proton energy by 4.1, close to the Newtonian factor of 4. Going from 0.2 to 0.4 multiplies it by 4.6. Going from 0.4 to 0.8 K multiplies it by 7. Going from 0.8 K to 0.99 K, a speed increase of only 24%, multiplies the proton energy by 9.1. The energy per particle diverges as the speed approaches c, and it does so without limit. There is no ceiling. There is no speed at which the incoming particles have reached their maximum severity, because the maximum does not exist. Think about what that means for a shield designer. In almost every other engineering domain, the hazard has a worst case. A bridge has a maximum design load. A pressure vessel has a burst pressure. A heat shield has a peak entry flux. The engineer identifies the extreme, adds a margin, and builds to it. A relativistic shield has no such number because the hazard is set by a parameter the mission wants to increase, and physics does not cap. The design question is never, what is the worst this shield must survive? It is always, what speed can this shield afford? Which turns the entire vehicle architecture into an argument about cruise velocity conducted in the language of stopping power. There is a further complication in the composition of what is arriving. The interstellar medium is not pure hydrogen. By number, it is about 90% hydrogen and about 9% helium, with roughly 0.1% everything else: carbon, nitrogen, oxygen, magnesium, silicon, iron. Helium arrives with 4 times the mass of hydrogen, and therefore 4 times the energy at the same speed. At half of light speed, Each helium nucleus carries about 577 million electron volts. The heavier elements are far rarer, but individually far more destructive. An iron nucleus at half of light speed arrives with about 8.1 billion electron volts, and heavy ions do a category of damage to materials that protons do not. So the beam striking the bow is not monoenergetic and not single species. It is a mixed ion beam, dominated by protons in number, with a helium component carrying a disproportionate share of the energy, and a trace heavy ion component that produces the most severe individual events. This is the environment. Now we can ask what it does to a person. The dose numbers are the part of this subject that most reliably surprises people, and they come primarily from one careful piece of work. Oleg Semyonov, working at Stony Brook, published an analysis titled Radiation Hazard of Relativistic Interstellar Flight in Acta Astronautica in 2009. It remains the reference treatment. It evaluates both the oncoming interstellar gas and the cosmic ray background, accounts for relativistic aberration, and estimates the shielding required. Its central conclusion is that above roughly 3/10 of light speed, the dominant radiation hazard is not cosmic rays at all. It is the interstellar gas, the ordinary cold, thin hydrogen that was harmless at rest and has been converted by the ship's own velocity into a directed particle beam. The estimated unshielded dose rate at 1/10 of light speed is approximately 60 rem per second. To calibrate that, the occupational limit for radiation workers on Earth is about 5 rem per year, and 10 rem per year is often quoted as an upper bound for a tolerable career exposure in a high-risk profession. At 60 rem per second, an unshielded hull absorbs an entire year's permitted dose in about 1/6 of a second. In 1 minute, it absorbs 3,600 rem, several times the dose that is reliably fatal to a human being within weeks. At 1/10 of light speed, the speed at which interstellar travel first becomes institutionally imaginable. As speed rises, the dose rate rises steeply and then approaches a plateau. Estimates in this literature converge on something in the region of 10,000 rem per second at speeds around 8/10 of c, a figure Semyonov compares to standing inside an operating reactor core. These are estimates, and they should be treated as such. They depend on the assumed medium density, which we established is uncertain by a factor of 10. They depend on the assumed geometry and on the model used to convert particle flux into biological dose. Different assumptions shift them by factors of a few. What they do not do is shift them by the 6 orders of magnitude that would be needed to make an unshielded relativistic hull survivable. And the plateau is not the good news it might sound like. It arises because at very high gamma, the incoming protons become so energetic that they pass through a given thickness of material without depositing all of their energy locally. They punch through rather than stopping. That is not protection. It is the hazard moving deeper into the ship, past the hull, past the shield, into the compartments and the crew and the electronics behind them. A dose that stops rising because the particles have stopped stopping is not a dose that has been solved. The saturation effect deserves to be understood properly because it is the single most counterintuitive feature of the relativistic radiation environment. When a charged particle passes through matter, it loses energy primarily by ionizing the atoms it passes. The rate of that loss depends on the particle's speed in a way described by the Bethe formula, and the important feature is that it is not monotonic. A slow proton deposits its energy over a short distance. As proton energy increases, the stopping power falls, reaches a broad minimum, and then rises very slowly again at extreme energies. Particles near that minimum are called minimum ionizing particles, and they are the most penetrating things a shield has to deal with. For protons in ordinary matter, the minimum sits at a kinetic energy of roughly 2 to 3 billion electron volts. Look at where that lands on our table. 2 to 3 billion electron volts corresponds to a ship speed of about 0.95 K to 0.97 Ceph, which means that as a starship accelerates from 0.1 K toward 0.95 K, the incoming protons become steadily more penetrating, not less. They carry more energy and they give up less of it per centimeter of shield. The practical consequence is that shield thickness requirements rise faster than the dose does. To stop a 4.7 million electron volt proton at 0.1 degrees Celsius, a few millimeters of dense material suffices. To stop a 145 million electron volt proton at half of light speed, you need tens of centimeters. To stop a multi-billion electron volt proton at 0.95 key, you need meters. And even then, a fraction of the flux passes through. Semyonov's estimates put roughly 2 centimeters of titanium as adequate near 3/10 of light speed and describe the required thickness as escalating to meters by 8/10. For cosmic ray protection, he discusses a spherical shell of water approximately 5 meters thick, and then observes that even this is insufficient against the secondary gamma and muonic radiation the shell itself produces. That last clause is the sentence to hold on to. The shield does not merely fail to stop everything. It manufactures a new problem out of what it does stop. There is a version of this hazard that gets discussed occasionally and should be set aside as an exaggeration. It is sometimes said that a relativistic ship faces a wall of gamma rays, a solid front of hard radiation that no material can survive. That framing overstates the case. What arrives is a mixed ion beam, and what it produces inside the shield is a shower of secondaries with a broad energy spectrum. It is severe, it is continuous, and it is deeply difficult to engineer around. It is not a wall, and describing it as one obscures the actual problem, which is subtler and in some ways worse. The actual problem is that the material you interpose becomes a source. Secondary radiation is the reason that adding shielding mass does not monodically improve crew safety, and it is the most important single fact in relativistic vehicle design. When a high-energy proton strikes a nucleus in the shield, it does not simply stop. At energies above a few 100 million electron volts, it undergoes spallation. The target nucleus fragments, ejecting neutrons, protons, alpha particles, and lighter nuclei in a cascade. Each of those fragments carries energy. Many of them travel deeper into the shield. Some of them cause further reactions. The result is a particle shower, initiated at the shield's outer surface and propagating inward, in which one incoming particle becomes many outgoing ones. The neutrons are the worst of it. Neutrons are electrically neutral, which means they are unaffected by magnetic fields and pass through material without the continuous ionization losses that slow charged particles. A neutron produced 2 centimeters into a titanium shield can travel through the remaining shield, through the pressure hull, and into the crew compartment, where it deposits energy in tissue with a biological effectiveness several times that of an equivalent dose of protons. At extreme energies, the shower includes pions, which decay into muons. Muons are extraordinarily penetrating. They are the reason cosmic rays are detectable in deep underground laboratories, hundreds of meters below the surface. A muon flux generated inside your own shield is a flux you cannot shield against with any thickness you can afford to carry. So the design curve has a shape that surprises people who have not encountered it. As you add shielding, the primary dose falls quickly, but the secondary dose rises because more shield mass means more nuclei available to be struck and more shower material to be generated. The total dose falls, reaches a minimum, and then flattens, and in some geometries for some particle energies, it rises again. There is an optimum shield thickness, and adding mass beyond it makes the crew's situation worse while making the ship heavier, which makes the mass ratio worse, which makes the mission worse. This is the thing nobody says plainly enough when the topic comes up in conversation. You cannot solve relativistic radiation by building a thicker wall. The wall is part of the problem. Past a certain thickness, the wall is most of the problem. Terrestrial reactor shielding solves this by layering a high atomic number material to attenuate gammas, then a hydrogen-rich material to moderate neutrons, then a neutron absorber such as boron. That layered approach works, and a starship would use something like it. But every layer is mass, and mass on a relativistic ship is not measured in tons. It is measured in the exponent of the mass ratio. The mass recursion is where radiation shielding stops being a radiation problem and becomes a propulsion problem. And it is the mechanism by which a manageable-looking requirement becomes an unaffordable one. Follow the chain. The crew needs protection, so the ship carries a shield. The shield has mass. That mass must be accelerated to cruise speed, which requires propellant according to the exponential rocket equation. The propellant has mass. That propellant must be itself be accelerated, requiring more propellant. And if the mission intends to stop, all of it must be carried through the cruise and the mass ratio squares. Now add the feedback. A heavier ship for a given engine accelerates more slowly. Slower acceleration means a longer acceleration phase. A longer acceleration phase means more time spent in the radiation environment, which means the shield must protect for longer, because shielding is about total accumulated dose, not just dose rate, argues for a thicker shield. The loop is not always divergent. For modest speeds and modest shields, it converges to a sensible answer, and this is exactly how spacecraft radiation shielding is designed today for missions to Mars and beyond. But the loop's convergence depends on the exhaust velocity, and we have already seen how brutally that parameter behaves. With a fusion drive at 0.05 K exhaust, every additional ton of shield at a 0.2 cruise requires roughly 57 additional tons at departure and 3,300 additional tons if the mission includes braking. A shield of 1,000 tons which is not an unreasonable figure for a layered structure protecting a habitable volume, becomes 3.3 million tons of departure mass by itself. There's a partial escape, and it is worth stating because it is the design most serious proposals converge on. You do not need to shield the whole ship. You need to shield the crew, and only from the forward direction. The oncoming beam arrives from almost exactly ahead. Relativistic aberration ensures this. At high gamma, even particles that were arriving from the side in the rest frame appear to arrive from near the bow. So a shield does not need to be a sphere. It needs to be a disc or a cone positioned forward with a crew compartment sitting in its geometric shadow. That reduces the shielded area enormously. A ship with a 10-meter radius forward shield presents about 314 square meters of shield, rather than the several thousand square meters of a full enclosure. It also introduces a constraint that will matter later. The ship must not turn. A vessel whose protection is a forward disc is protected only while it is pointed forward. Any maneuver that exposes a flank exposes the crew directly to the beam, which means attitude control is a life support function, and a ship that loses attitude control at relativistic speed loses its crew on a timescale of seconds to minutes. Magnetic deflection is the alternative to mass, and it is genuinely promising for part of the problem, which makes its specific failure mode all the more important to understand. The idea is straightforward. Charged particles curve in a magnetic field. If a ship generates a sufficiently strong field ahead of itself, incoming protons and helium nuclei are deflected around the crew compartment rather than absorbed by it. No mass is consumed. The field costs power, not propellant, and power is generally cheaper than mass on a relativistic vessel. Active magnetic shielding has been studied seriously for crewed Mars missions, where the particles of concern are solar energetic protons in the range of tens to hundreds of millions of electron volts. At those energies, achievable superconducting coils can produce meaningful deflection. At relativistic crews, two things degrade the concept. The first is rigidity. A particle's resistance to magnetic deflection is measured by its magnetic rigidity, which is proportional to its momentum. At high gamma, momentum grows without bound, so rigidity grows without bound. So the field strength required to deflect a given particle grows without bound. Deflecting a 5.7 billion electron volt proton, the arrival energy at 0.99 key, requires field and distance products that are orders of magnitude beyond deflecting a 100 million electron volt one. The coil that protects you at 0.2 key does very little at 0.9 key. The second failure is more fundamental, and it is the one that cannot be engineered away by building a stronger magnet. A large fraction of the interstellar medium in the local corridor is neutral. The local interstellar cloud is described as largely neutral hydrogen, and neutral atoms carry no charge. A magnetic field does not deflect them. It does not slow them. It does not see them at all. They pass through the field as if it were not there and strike the shield or the hull at full energy. There is a partial answer. Ionize the incoming neutrals ahead of the ship with a laser or electron beam so that the magnetic field can act on them. And it is a real proposal, but it requires ionizing a column of gas continuously across the ship's entire frontal area for the duration of the voyage, using energy that must be generated aboard in order to make particles vulnerable to a field that must also be generated aboard. There is also a structural cost that is easy to leave out of the accounting. A coil carrying enough current to deflect relativistic protons across a useful volume experiences enormous forces on itself. A magnetic field exerts pressure, and a field strong enough to matter here exerts pressure comparable to the strongest structural materials can resist. The coil does not merely need to exist, it needs to be held together against its own field, continuously, by structure that has mass, in a geometry that must remain precise while the ship is being eroded at the bow and heated from the front. And superconductors are among the least radiation-tolerant materials in an engineer's catalog. The property that makes them useful, a delicate ordering of electrons that vanishes above a critical temperature, current, or field, is disrupted by exactly the kind of lattice damage that energetic particles produce. A superconducting coil operating for 4 decades inside a relativistic particle flux is being slowly converted into an ordinary conductor, and an ordinary conductor at those currents is a heater. So magnetic shielding is not a replacement for mass. It is a supplement that reduces the required mass, works best at lower speeds, degrades in the environment it exists to defend against, and is blind to a substantial fraction of what is arriving. The composition of the medium deserves closer attention because the danger is not distributed the way the abundance is. By number, the local interstellar medium is roughly 90% hydrogen and 9% helium, with everything heavier making up about 0.1%. It is tempting to treat the heavy component as negligible. It is not, and the reason is that damage does not scale with number. Take the energy first. At a given speed, kinetic energy scales with mass. A helium nucleus is 4 times the mass of a proton, so at half of light speed it arrives with about 577 million electron volts against the proton's 145. Helium is 9% of the particles, but about 29% of the incoming energy. Now take the damage mechanism, which scales differently again. The rate at which a charged particle deposits energy along its path, its linear energy transfer, scales roughly with the square of its nuclear charge. Helium, with charge 2, deposits energy 4 times as densely as a proton of the same velocity. Carbon, with charge 6, deposits it 36 times as densely. Iron, with charge 26, deposits it 676 times as densely. Iron is roughly 1 atom in 30,000 in the interstellar medium. But each iron nucleus striking a shield at relativistic speed produces a damage track that no proton can produce. A narrow cylinder of intensely disrupted material in which chemical bonds are broken, crystal structure is destroyed, and in a biological context, both strands of a DNA molecule can be severed simultaneously by a single particle. That last point is the one that matters for a crew. Most radiation damage in tissue is repairable. A single-strand break in DNA has an intact template opposite it and cellular machinery that repairs it reliably. A double-strand break, produced by a densely ionizing heavy ion, has no template, and the repair is error-prone. This is why heavy ion exposure is weighted so heavily in radiation protection standards, and why the galactic cosmic ray component of deep space radiation is considered more dangerous per unit dose than its magnitude alone would suggest. For a relativistic ship, the heavy ions are not a background. They are the same medium as everything else, converted by velocity into a heavy ion beam whose individual events are qualitatively more destructive than the proton flux surrounding them. There is a parallel effect in materials, and it is the reason the heavy component matters even for an uncrewed probe. A proton passing through a solid displaces atoms one at a time along a sparse path, and most of those displacements heal. The lattice settles back into its original order. A heavy ion produces a continuous cylinder of displaced atoms dense enough that the region melts locally and resolidifies into a disordered state. In quartz and other ordered materials, that leaves a permanent etchable track. In semiconductors, a single heavy ion passing through a transistor can deposit enough charge to flip a bit, or, in the worst case, trigger a self-sustaining current that destroys the device outright. Spacecraft electronics are already designed against this. Radiation-hardened processors, error-correcting memory, and triple redundant voting systems exist precisely because a single galactic cosmic ray can corrupt a computation. What changes at relativistic speed is the rate. The galactic cosmic ray flux is a background of a few particles per square centimeter per second. The medium converted by velocity into a heavy ion beam delivers at 0.1 atoms per cubic centimeter and half of light speed, something in the region of 10 to the ninth heavy nuclei per square meter per second, a rate that turns a rare, correctable event into a continuous one. The medium is 90% hydrogen. The problem is not 90% hydrogen. Material damage, as distinct from biological dose, has been studied specifically for relativistic flight, and the results are unusually concrete. In 2017, Thiem Hoang, Alex Lazarian, Blakesley Burkhart, and Avi Loeb published a paper in the Astrophysical Journal titled "The Interaction of Relativistic Spacecrafts with the Interstellar Medium." They were motivated by Breakthrough Starshot, a gram-scale sail traveling at 2/10 of light speed toward Alpha Centauri, and they quantified what the gas and dust would actually do to it. The gas result is track formation. Incoming heavy nuclei, the same carbon, oxygen, magnesium, and iron we have just discussed, produce damage tracks in the spacecraft surface. Their finding is that after traversing a hydrogen column density of about 2 times 10 to the 18th atoms per square centimeter, gas bombardment can damage a quartz surface to a depth of approximately 0.1 millimeters. 1/10 of a millimeter does not sound like much, and for a large vessel it is not. For a sail a few micrometers thick, and Starshot's sail must be extraordinarily thin to be accelerated at all. 1/10 of a millimeter is not damage. It is the entire structure, many times over. The material dependence is significant and encouraging. Hoang and colleagues found the effect considerably weaker for graphite than for quartz. Carbon-based materials tolerate this environment better, which is a genuinely useful engineering result. The choice of bow material is not a detail. It is a factor of several decisions made before anything else is designed. It is worth pausing on that column density because it connects the laboratory number to the voyage. 2 times 10 to the 18th atoms per square centimeter, at a density of 0.1 atoms per cubic centimeter, corresponds to a path length of about 2 times 10 to the 19th centimeter, which is about 21 light years. The distance to Alpha Centauri is 4.37 light years. At the local density of a tenth of an atom per cubic centimeter, the actual column to Alpha Centauri is about 4.1 times 10 to the 17th atoms per square centimeter, roughly a fifth of the value used for that damage estimate. The published figure is therefore conservative in the sense of assuming a denser path, and the authors chose it deliberately because the corridor is not guaranteed to be as thin as our immediate neighborhood. That is the correct instinct, but it also means the honest way to state the result is this. A quartz surface flying to Alpha Centauri at 0.2 of light speed accumulates gas damage on the order of 1/100th to 1/10 of a millimeter, depending on a density we do not know precisely, and every 100 meters of additional density the mission encounters makes it worse. That is the gas. The dust is a different order of problem. Before turning to dust, one more component of the radiation environment needs to be accounted for because relativistic motion does something to it that has no equivalent at rest. Galactic cosmic rays are already present. They are atomic nuclei accelerated to extreme energies by supernova shocks and other astrophysical processes, and they permeate the galaxy. In the solar system, the cosmic ray flux delivers a dose of roughly 60 rem per year to an unshielded object in interstellar space, which, as Semyonov noted, is already several times the annual limit for a radiation worker on Earth, and is a known constraint on any long-duration crewed mission regardless of speed. Cosmic rays arrive isotropically. From a stationary vantage point, they come from all directions in roughly equal numbers, which means a spherical shield is the natural geometry, and there is no preferred direction to defend. Move at relativistic speed, and the isotropy collapses. Relativistic aberration transforms the arrival directions, sweeping the flux forward into a cone whose opening angle narrows as gamma rises. The same effect that concentrates starlight ahead of a fast ship concentrates cosmic rays ahead of it. The geometry is precise. A particle arriving from exactly A beam in the rest frame, 90 degrees to the direction of travel, appears in the ship's frame to arrive at an angle whose cosine equals beta. At half of light speed, that is 60 degrees from the bow. At 0.9 degrees Celsius, 25.8 degrees. At 0.99 degrees Celsius, 8.1 degrees. At 0.99 degrees Celsius, 2.6 degrees. Read that as a statement about hemispheres. At 0.99 C, half of the entire sky, everything that was in front of the ship's midplane, has been compressed into a forward cone, barely 8 degrees across, and a substantial portion of what was behind has been swept into the forward hemisphere as well. There are two consequences, and they point in opposite directions. The unfavorable one is that the forward flux increases dramatically, both because more of the sky is contributing to it and because the arriving particles are Doppler boosted in energy. The bow of a relativistic ship faces a cosmic ray intensity far above the isotropic background. The favorable one is that the rear and the flanks become genuinely quiet. aberration takes the flux that would have struck the sides and moves it forward into the region already defended by the forward shield. This is the geometric argument for the shadow architecture. One massive forward shield, a long thin ship in its geometric shadow, and very little mass anywhere else. It is the shape almost every serious relativistic design converges on. It also explains a detail that sounds like a design preference and is actually a physical requirement. Relativistic ship concepts are always drawn long, not because length is aesthetically appropriate to interstellar travel, but because the shadow behind a shield of fixed radius is a cylinder, and the only way to fit useful volume into a narrow cylinder is to extend it backward. Every meter of additional radius on the shield costs mass proportional to the square of the radius. Every meter of additional length behind it costs almost nothing because the material there is already protected. So the vessel becomes a needle with a plate at the front, and the crew lives somewhere along the needle, as far from the plate as the structure allows. Because the secondary shower generated inside the shield falls off with distance behind it, and separation is the one form of protection that costs no mass at all. That is the shape the dust environment is about to complicate. There is a consequence of stopping all those particles that receives far less attention than it deserves, and it follows from a principle so basic that it is easy to skip past. Energy that is absorbed does not disappear. Every proton the shield stops deposits its kinetic energy in the shield. Every helium nucleus, every iron nucleus, every secondary neutron that is finally captured, all of it becomes heat. The shield is not a filter, it is a target, and a target that absorbs a continuous particle beam becomes a heat source whose output is set by the beam power. The arithmetic is direct. Multiply the particle flux by the energy per particle, and you have watts per square meter. At a tenth of light speed, with a density of 0.1 atoms per cubic centimeter, the forward face absorbs about 2.3 watts per square meter. That is negligible, comparable to standing in weak sunlight filtered through cloud, and a passive radiator handles it without comment. At 0.2 of light speed, 19 watts per square meter. Still modest, at half of light speed, 403 watts per square meter. That is now a third of the solar constant at Earth's orbit, arriving continuously on a surface that has no atmosphere to convect it away and no night side to cool during. At 0.8, about 4 kilowatts per square meter, 3 times the intensity of full sunlight at Earth. At 0.9 C, 12 kilowatts per square meter. At 0.99 C, 193 kilowatts per square meter. That is roughly 140 times the solar constant, delivered continuously to the forward face of the ship for the duration of the cruise. For scale, the peak heat flux on a spacecraft heat shield during a steep Earth atmospheric entry is in the range of a few megawatts per square meter. But that lasts for a couple of minutes, and then the vehicle has landed. This lasts for years, and these figures assume a density of a tenth of an atom per cubic centimeter. In a corridor 3 times denser, triple them. Note what has just happened to the shield's job description. It began as a radiation shield. It has become a radiation shield that is also continuously absorbing a substantial power flux and must dispose of that power without conducting it into the crew compartment sitting directly behind it. A shield that stops the beam and then cooks the ship has not protected anyone. There is a genuine perversity in the arrangement. The better the shield is at its primary job, the more completely it stops the incoming particles, the more heat it generates. A shield that let everything through would run cool and kill the crew with radiation. A shield that stops everything runs hot and kills the crew with temperature. The design has to find a point between those two, and the point moves as the ship accelerates. Getting rid of that heat is a harder problem in space than almost anywhere else, because there's exactly one mechanism available. On Earth, heat leaves a hot object three ways: conduction into whatever it touches, convection into the surrounding fluid, and radiation. In vacuum, the first two are unavailable. There is nothing to conduct into and nothing to convect. Every joule a spacecraft absorbs must eventually leave as electromagnetic radiation from a surface, or it stays. The governing relationship is the Stefan-Boltzmann law. The power radiated per square meter is proportional to the fourth power of absolute temperature. That fourth power is the entire design space. A radiator at room temperature, about 300 Kelvin, emits roughly 460 watts per square meter if it is a perfect emitter. A radiator at 600 Kelvin emits about 7,350 watts per square meter. Doubling the temperature multiplies the emission by 16, which is why every serious thermal design in spaceflight tries to reject heat at the highest temperature the hardware tolerates. Now apply it. At 0.5 Ken, the forward face is absorbing 403 watts per square meter. If the radiator runs at 300 Kelvin, it needs roughly 1 square meter of radiator per square meter of bow, which is manageable. At 0.99 Ken, the bow absorbs 193 kilowatts per square meter, and a 300 Kelvin radiator would need about 420 square meter of surface for every square meter of frontal area. Run the radiator at 1000 Kelvin instead, and that falls to about 3.4 square meter per square meter of bow. A dramatic improvement, and the reason high-temperature radiators dominate these designs. But a 1000 Kelvin radiator is a glowing structure, and glowing structures are made of materials that must survive 1000 Kelvin continuously for years while being irradiated. There is a second problem with radiators on a relativistic ship, and it is geometric. Radiator area must be large, thin, and exposed. Shield geometry demands that everything sit in the narrow shadow behind a forward disk. Those two requirements are in direct conflict. A radiator wide enough to reject the heat sticks out beyond the shield's shadow, and anything outside the shadow is being struck by the beam directly. The resolution most designs adopt is to run the radiators as long, thin fins trailing aft, parallel to the direction of travel, presenting almost no frontal area while presenting a large lateral area to empty space. This works, and it is why relativistic ship concepts tend to look like a shield, followed by a spine, followed by a very long set of vanes. It also means the ship is structurally committed to its orientation in a second way. The thermal design assumes the fins are edge-on to the flow. Turn the ship and the radiators become collectors. Everything on a relativistic vessel points the same direction, permanently, and everything depends on it continuing to. Dust changes the character of the problem entirely, because gas is a continuous load, and dust is a series of discrete events. The interstellar medium contains solid particles, grains of silicate and carbonaceous material, condensed in the atmospheres of dying stars and in the ejecta of supernovae, then processed for millions of years in the interstellar radiation field. They are what makes the dark lanes visible across the Milky Way. They absorb and scatter starlight, which is how we know they are there, and roughly what they are made of. The standard description of their sizes is the MRN distribution, named for a 1977 paper by John Mathis, William Rumpel, and Kenneth Nordzeek. It describes the grain population as a power law. The number of grains per unit size interval falls off as size to the power of minus 3.5 across a range from roughly 0.005 micrometers to roughly 0.25 micrometers. Two features of that distribution matter enormously for a starship. The first is that it is steep. A power law with an index of minus 3.5 means small grains dominate overwhelmingly by number. For every grain of 1/10 of a micrometer, there are roughly 3,000 grains of 100th of a micrometer. The population a ship encounters is, in terms of sheer counting, almost entirely made of the smallest particles. The second is that the large end is poorly constrained. The MRN power law was fitted to the wavelength dependence of interstellar extinction, how much starlight of different colors is absorbed. That method is sensitive to grains comparable in size to the wavelength of light, which means it constrains the population up to a few tenths of a micrometer well, and says very little about what lies beyond. Larger grains exist. We know they exist because spacecraft have detected them directly. The Ulysses mission spent 16 years measuring interstellar dust passing through the solar system, and Kruger and colleagues used that data set to constrain the local grain mass distribution and the gas-to-dust mass ratio. Those measurements found grains extending to masses well above what the extinction-fitted distribution would predict, because a large grain contributes almost nothing to extinction per unit mass, while contributing everything to an impact. The overall dust content is usually expressed as a gas-to-dust mass ratio of about 100, meaning roughly 1% of the interstellar medium's mass is in solid grains. At 0.1 hydrogen atoms per cubic centimeter, that corresponds to a dust mass density of about 1.7 times 10 to the minus 28th grams per cubic centimeter, which is a number so small that writing it out feels almost beside the point. And yet the entire risk profile of a relativistic mission lives inside that number because of what velocity does to a solid object. The impact energy ladder is the clearest way to see why dust dominates the failure modes, and it only requires the same formula we have been using all night. A grain's kinetic energy in the ship's frame is gamma minus 1 times its mass times c squared. The grain masses are tiny. The c squared is not. Take a silicate grain with a density of about 2,000 kilograms per cubic meter, a reasonable figure for interstellar silicate and carbonaceous material, and stated explicitly because the answer scales directly with it. A grain of 0.1 micrometers radius has a mass of about 8.4 times 10 to the minus 18th kilograms. At 2/10 of light speed, it delivers 0.0155 joules. That is a small number, comparable to dropping a paperclip a few centimeters. But it is delivered into a volume perhaps a micrometer across in a time of order 10 to the minus 17th seconds, which produces local energy densities that vaporize the material outright. A grain of 1 micrometer radius has a mass of about 8.4 times 10 to the minus 15th kilograms. At 2/10 of light speed, 15.5 joules. That is the energy of a pistol bullet deposited in a point. A grain of 10 micrometers, still far too small to see, roughly the size of a red blood cell, carries 15,500 joules at 2/10 of light speed. That is the muzzle energy of a heavy rifle. A grain of 100 micrometers, about the width of a human hair, carries 1.55 times 10 to the 7th joules at 2/10 of a light speed. That is 15.5 megajoules, equivalent to about 3.7 kilograms of TNT, delivered by a particle you would struggle to see without magnification. Raise the speed and every figure climbs. At half of light speed, the 100 micrometer grain delivers 1.16 times 10 to the 8th joules, about 28 kilograms of TNT. At 9/10 of light speed, 9.7 times 10 to the 8th joules, roughly 230 kilograms of TNT. Sit with the shape of that ladder for a moment. 100-fold increase in grain radius is a 1,000,000-fold increase in mass, and therefore a 1,000,000-fold increase in impact energy. The distribution is steep, so large grains are rare. But the energy is cubic in radius, so the rare ones carry essentially all of the destructive potential. It is worth being explicit about what those energies do on contact, because the word impact carries misleading associations. At a fifth of light speed, a grain does not dent, chip, or crack the surface it strikes. The energy per atom in the collision exceeds the binding energy holding the material together by several orders of magnitude, which means the interaction is not mechanical at all. Both the grain and a region of the target are converted directly to plasma in a time far shorter than the material can respond to structurally. The crater is not excavated. It is vaporized into existence, and the surrounding material is driven outward by the pressure of that vapor. For the smallest grains, this is a microscopic event that removes a few million atoms and nothing more. For a 10 micrometer grain, it is a localized explosion inside the material, producing a shock wave that travels outward and can spall material off the back face of a plate even when nothing penetrates it. That spalled material becomes a secondary projectile inside the ship, traveling at hundreds of meters per second, which is the mechanism by which armor that stops a projectile can still injure what is behind it. This is the signature of a hazard that is difficult to design against. The average impact is negligible. The expected number of large impacts over a voyage is small, and the consequence of one large impact is catastrophic. Statistically, the ship is fine. Individually, the ship is a wager. Those impacts do two different kinds of damage, and separating them clarifies which one is an engineering problem and which one is a risk problem. The first is erosion. Small grains arriving constantly remove material from the bow atom by atom. Each impact vaporizes a microscopic crater's worth of surface. No single event matters. The cumulative effect over a voyage is a steady thinning of the forward face, entirely predictable, entirely calculable from the density and the exposure. The second is penetration. A large grain does not erode. It punches. The energy deposited by 100 micrometer grain at 2/10 of light speed is not spread over a surface. It is deposited along a line, driving a vapor jet through whatever is in front of it, potentially all the way through the ship. Erosion is a budget item. Penetration is a coin flip. Erosion can be engineered against with straightforward tactics. Make the bow thicker. Make it out of a material with a high sublimation energy. Accept a known loss rate and carry enough sacrificial material to survive it. The mission planner can calculate the required thickness, add margin, and be confident. Penetration cannot be engineered against in the same way because the energies involved exceed what any thickness of any material can stop through simple bulk. A grain arriving at 1/5 of light speed does not care about material strength. Chemical bond energies are of order a few electron volts per atom. The impacting grain carries energy per atom that exceeds this by orders of magnitude. On impact, both the grain and the region of the target it strikes are converted to plasma immediately. Strength is not a parameter in that interaction. Only mass per unit area is. And here's the thing that makes this genuinely difficult rather than merely expensive. The mass per unit area required to stop a large grain is enormous, and the probability of encountering one is low. Every kilogram of bow armor you add is a kilogram that must be accelerated at the full mass ratio penalty in exchange for protection against an event that will probably not occur. That is an unpleasant kind of decision. It is not a technical question with a technical answer. It is a question about how much of the mission budget a designer is willing to spend ensuring against a low probability total loss on a voyage where there is no rescue, no repair mission, and no second attempt. Spacecraft designers make risk versus mass decisions constantly, and they have well-developed methods for it. What is different here is that the usual escape routes are absent. There is no abort. There is no redundancy that helps, because a grain that destroys the primary structure destroys the backup mounted behind it. There is no inspection and repair, because the damage occurs at a closing speed that gives no warning and the ship cannot slow down to assess it. The honest description is that a relativistic mission carries an irreducible probability of instantaneous, unannounced, total loss, and that this probability is set by a population of objects we have characterized poorly. The erosion figure has been calculated for a specific mission, and it is worth quoting exactly because it is one of the few numbers in this field that comes from a detailed physical model rather than an estimate. Hoang, Lazarian, Burkhardt, and Loeb, in the same 2017 paper, computed dust bombardment as well as gas bombardment. Their result, for a spacecraft speed of 2/10 of light speed, dust impacts erode a surface layer approximately 0.5 millimeters thick after the spacecraft has swept through a hydrogen column density of about 3 times 10 to the 17th atoms per square centimeter, assuming the standard gas-to-dust ratio. Compare that column to the Voyage. At a density of 1/10 of an atom per cubic centimeter, the hydrogen column to Alpha Centauri across 4.37 light years is about 4.1 times 10 to the 17th atoms per square centimeter. The mission and the damage figure are therefore approximately the same voyage. Flying to Alpha Centauri at 2/10 of light speed removes something in the region of 0.5 millimeter to 0.7 of a millimeter from the forward face of the vehicle. That number lands very differently depending on what you are flying. For a Starshot sail, a reflective membrane whose thickness must be measured in fractions of a micrometer for the laser to accelerate it, 0.5 millimeter is 1,000 times the entire structure. The sail is not eroded. The sail does not exist by the time it arrives. This is precisely why the paper was written, and it is why Starshot's engineering discussion includes proposals to fold the sail behind the payload after acceleration, to spin the craft so no single element is continuously exposed, or to accept the sail's loss and protect only the chip. For a large crewed vessel, 0.5 millimeter off the bow across a 40-year cruise is by itself trivial. A ship massing thousands of tons carries a forward shield measured in tens of centimeters at minimum. Losing 0.5 millimeter of it is not a design driver, but scale the mission. Erosion is proportional to column density, which is proportional to distance traveled. A voyage of 43 light years, 10 times the distance to Alpha Centauri, removes 10 times as much, 5 to 7 millimeters. A voyage of 400 light years removes 5 to 7 centimeters. A voyage across the galaxy at 30,000 light years removes something in the region of 3 to 5 meters of forward material, and that is at 2/10 of light speed. Erosion depth scales strongly with impact energy, so a ship cruising at 1/2 or 9/10 of c removes considerably more per unit distance. There is the shape of the trade again. The distances that make relativistic speed worthwhile are precisely the distances at which erosion stops being a rounding error and becomes a mass budget of its own, a slab of sacrificial material at the front of the ship whose only function is to be gradually destroyed, and which must be accelerated to cruise speed at the full exponential cost. The rare grain problem is the part of this that resists calculation, and it deserves to be examined honestly rather than dismissed or dramatized. Start with the statistics. Consider a ship with a forward cross-section of 100 square meters, a disk about 11 meters across, flying 4.37 light years to Alpha Centauri. The volume of space swept out is 100 square meters multiplied by 4.1 3 times 10 to the 16th meters, which is 4.13 times 10 to the 18th cubic meters. Now the question is how many grains of a given size sit in that volume. For grains near the top of the well-measured MRN range, around 0.25 micrometers, the number density is high enough that the ship encounters an enormous number of them. This is the erosion regime, and it produces the smooth, predictable loss we have just discussed. For grains around 10 micrometers, the number density is far lower, but the swept volume is so large that encounters remain likely. Each of those delivers 15,500 joules at 2/10 of light speed, a serious but survivable event for a large armored bow, producing a crater and a shockwave rather than a penetration. For grains around 100 micrometers, the expected number of encounters over a single interstellar crossing is genuinely uncertain because the number density at that size is not measured with confidence. Extinction-based fits predict essentially none. Direct detections by Ulysses and by dust instruments on other missions found more large mass particles than the extinction fits imply. So the honest statement is that the expected number of catastrophic impacts on an interstellar crossing is somewhere between effectively 0 and of order 1, and the width of that range is a measurement problem, not a physics problem. This is a deeply uncomfortable position for mission design, and it is uncomfortable in a specific way. It is not that the risk is high, it is that the risk is unquantified, and the consequence is total. Compare it to something familiar. Aviation safety works because the failure modes are known. The probabilities are measured across billions of flight hours, and the consequences of individual component failures are contained by redundancy. None of those three conditions holds here. The failure mode is known only in outline. The probability rests on a grain population we have sampled in one location, in one direction, over 16 years, by an instrument the size of a dinner plate, and the consequence is not contained by anything. There is one genuine mitigation, and it is worth naming. The same measurement problem is solvable. A dedicated precursor mission, a small, fast probe sent along the intended corridor decades ahead, instrumented specifically to count large grains, would convert this from an unquantified risk into a quantified one. That is an unglamorous mission with no destination and no images, and it is probably the single most valuable thing a civilization could fly before committing a crew. The standard defense against hypervelocity impact does not work at these speeds, and understanding why is instructive because it shows how thoroughly relativistic velocity breaks engineering intuition. The Whipple shield is one of the more elegant ideas in spaceflight. Fred Whipple proposed it in 1947, and it has protected essentially every crewed spacecraft since. The concept is a thin outer bumper standing off some distance from the main hull. An incoming particle strikes the bumper and is destroyed by the impact, but so is the bumper locally. Both are converted into a spray of vapor and fragments. That spray expands as it crosses the standoff gap, so by the time it reaches the main wall, the same total momentum is distributed over a much larger area, and the wall survives. The shield works by trading concentration for area. It does not stop the particle. It disperses it. Two things at relativistic speed defeat this. The first is the standoff time. The dispersal only helps if the debris cloud has time to spread before it reaches the rear wall. At orbital impact speeds of about 10 kilometers per second, a 10 centimeter standoff gives the cloud about 10 microseconds to expand. An expansion at a few kilometers per second spreads it over several centimeters. That is enough. At 0.2 of light speed, the same 10 centimeter gap is crossed in 1.7 nanoseconds. The debris cloud expands laterally at speeds set by the material's thermal velocity, still measured in kilometers per second. So in 1.7 nanoseconds, it spreads by a few micrometers. The spray arrives at the rear wall, essentially as concentrated as it left the bumper. The shield has converted one projectile into one projectile. To recover the same dispersal ratio, the standoff distance would need to scale with the speed ratio, meaning a gap of roughly 2 kilometers rather than 10 centimeters. A ship with a bumper 2 kilometers ahead of its hull is not a spacecraft with a shield. It is a formation. The second failure is more basic. A Whipple bumper works because the bumper survives long enough to disrupt the projectile. At relativistic energies, the projectile passes through thin material so quickly that it deposits only a fraction of its energy there. A tenth of a millimeter aluminium bumper does not shatter 100 micrometer grain arriving at a fifth of light speed. It removes a few percent of its energy and lets the rest continue. There is a partial version that does help, and it is used in serious designs. A very large standoff, kilometers, maintained by flying a separate unmanned sacrificial vehicle ahead of the crewed ship. That works in principle. It also requires station keeping between two vessels at relativistic speed across a gap where a light signal round trip takes microseconds and any relative velocity error accumulates over decades. Since interception fails, the surviving strategies are all about geometry, and several of them are genuinely clever. The first is the sacrificial bow. Accept that the forward face will be destroyed and design it to be destroyed usefully. Put the cheapest, densest, most expendable material you have at the very front. Water ice is a recurring proposal because it is abundant, cheap to acquire in the outer solar system, has excellent hydrogen content for neutron moderation, and can be shaped without manufacturing. An ice plug several meters thick at the nose serves as radiation shield, thermal mass, dust armor, and, in some designs, propellant reserve. The elegance is that the same mass does 4 jobs. The limitation is that it is still mass, and mass is still the exponent. The second is presenting the smallest possible frontal area. Every square meter of bow is a square meter of erosion, a square meter of radiation collection, and a square meter of impact probability. So the relativistic ship wants to be a needle. Minimal cross-section, maximum length, everything shadowed behind a small forward shield. This is the exact opposite of the shape efficient for radiators, habitable volume, or structural stiffness, and the resulting design is a compromise between a spike and a fan. The third is rotation. Spinning the vehicle about its axis of travel distributes erosion evenly around the bow, rather than concentrating it wherever the flow happens to strike. For a sail or a thin structure, spin also allows the exposed element to be a different piece of material at each moment, spreading damage across the whole rather than boring a hole through one part. Starshot's engineering discussions include spin for exactly this reason. The fourth is a shape that deflects rather than absorbs. A steeply angled conical nose presents incoming particles with a grazing incidence rather than a normal one. At grazing incidence, more of the impact energy goes into material ejected sideways and less into the structure. This is the same principle that makes sloped armor effective, and it is one of the few defensive concepts that survives the transition to relativistic speed intact, because it depends on geometry rather than on material response time. None of these is a solution. They are all mitigations, and they share a common property. Each of them reduces the damage rate by some factor of a few, while the hazard itself scales with a gamma that has no upper bound. A defense that improves your situation by a factor of 3 is valuable at zero point 0.2 key and irrelevant at 0.99 key. There is a fifth approach that is qualitatively different, and it deserves mention because it is the only one that attacks the problem rather than absorbing it. Clear the path ahead. The proposal is to fly a beam, a laser, or a stream of charged particles forward from the ship, far enough ahead that grains encountering it are heated, charged, ablated, or deflected before the ship reaches them. Against small grains, this could work. A sufficiently intense beam vaporizes a tenth of a micrometer particle outright. Against a 100 micrometer grain, the required energy is the grain's entire vaporization enthalpy delivered in the light travel time available, and the ship must supply that from its own reactor while also supplying everything else. The deeper limitation is detection. To clear a grain from the path, the ship must know the grain is there. A 100 micrometer dark silicate particle against interstellar background at a range of even a few thousand kilometers reflects almost nothing. At 2/10 of light speed, 1,000 kilometers of warning is 16 milliseconds. The detection problem is not merely difficult. It is a search for an unilluminated object smaller than a grain of sand, at a range where it subtends a few nanoradians, with milliseconds to act. The mitigations buy speed. They do not buy unlimited speed. Every one of them has a velocity above which it stops mattering. There is a final, honest thing to say about the dust and gas environment, and it is the sort of statement that rarely makes it into an optimistic account. We have never sampled the corridor we would fly through. Everything we know about the local interstellar medium comes from 3 sources, and each has a specific limitation. The first is absorption spectroscopy, measuring how the light of distant stars is dimmed and reddened by intervening material. This is powerful and it covers enormous volumes, but it measures a line of sight average. It cannot tell you whether the material is spread evenly along the path or concentrated in a single dense clump halfway along it. For a starship, that distinction is the difference between a manageable cruise and a wall. The second is in situ measurement by spacecraft. Ulysses counting dust grains for 16 years, New Horizons measuring hydrogen density, the Voyagers reporting plasma density beyond the heliopause. These are direct, unambiguous, and precious. They are also all taken from within a few tens of astronomical units of the sun, in a region that the sun's own magnetic field and solar wind have been actively modifying for the entire history of the measurement. The heliosphere excludes smaller charged dust grains and modulates the plasma. What passes through it and reaches our instruments is a filtered sample of what is actually out there. The third is modeling, inferring the structure of the local bubble and the local interstellar cloud from the combination of the first 2, plus theory. Good models exist. They are consistent with the data. They are also fitting a small number of measurements to a large volume. So the sentence that should accompany every erosion calculation and every dose estimate in this episode is this. The density is 1/10 of an atom per cubic centimeter with an uncertainty of a factor of 10. The large grain population is constrained by one long duration measurement taken inside a magnetic cavity, and the specific path to any specific star has never been characterized at all. A mission designed against those uncertainties has to carry margin, and margin is mass, and mass is the exponent. A factor of 10 uncertainty in density does not produce a factor of 10 uncertainty in mission cost. It produces a factor of 10 uncertainty in shield thickness, which propagates through the rocket equation into something far larger. The most valuable thing that could be done for interstellar travel before any ship is built is not a better engine. It is a survey. Send small, cheap, fast instruments along the candidate corridors decades in advance and measure what is actually there. Convert the unknown into a number. That is not a dramatic proposal. It has no crew and no destination and returns nothing but a table of densities and grain counts. It is also the difference between designing a ship and guessing at one. The medium is not the only thing a relativistic ship runs into. It also runs into light, and the light of the universe behaves in ways that become significant well before the crew notices anything else. The cosmic microwave background fills all of space. It is the cooled remnant of the hot early universe, and it currently sits at a temperature of 2.72548 Kelvin, a measurement made with extraordinary precision by the FIRAS instrument aboard the COBE satellite. It is the most uniform thing in existence, arriving from every direction at an intensity so low it corresponds to a few hundred photons per cubic centimeter, carrying a total energy density smaller than starlight. At rest, it is entirely harmless. It is the background against which everything else is measured. Move toward it and it blue shifts. The Doppler factor for head-on motion is the square root of 1 plus beta over 1 minus beta, and it applies to both the photon energy and the arrival rate. At a tenth of light speed, the factor is 1.106. The forward background appears at about 3.01 Kelvin instead of 2.73. Immaterial. At half of light speed, the factor is 1.732, and the forward temperature is 4.72 Kelvin. At 8/10, the factor is exactly 3, and the forward background reads 8.18 Kelvin. At 0.99 C, the factor is 14.1, and the forward temperature is 38.4 Kelvin. At 0.999 C, the factor is 44.7, and the forward background reads 122 Kelvin, comparable to the surface temperature of the outer solar system, radiating onto the bow of the ship from what used to be the emptiest and coldest thing in the universe. There is an important qualification. This is not a uniform sky temperature. Aberration and Doppler shift act together to produce a strongly direction-dependent pattern, hot ahead, cold behind, with a smooth gradient between. A thermometer at the bow reads one thing and a thermometer at the stern reads another, on the same vessel at the same time. The practical consequence is thermal rather than biological. Even 122 Kelvin is far below the temperatures produced by the particle flux we discussed earlier, so the blue-shifted background is not what limits the design. But it does eliminate an assumption every deep space thermal engineer relies on. that the sky is a 2.7 Kelvin heat sink you can always radiate into. At extreme gamma, the forward sky stops being a sink and becomes a source. The radiators can no longer face forward, and a ship whose radiators must all face aft, while its shield must face forward and whose crew must sit between them, is running out of directions. There is a second and subtler consequence for the science. The cosmic microwave background is the most precisely characterized signal in cosmology, and its tiny temperature variations encode the structure of the early universe. From a relativistic ship, that signal is transformed beyond recognition. The intrinsic pattern buried under a dipole thousands of times larger than the fluctuations themselves. The transformation is exactly calculable, so nothing is lost in principle. But a ship at high gamma is one of the worst possible platforms from which to measure the one background that fills all of space, which is a small and specific example of the general rule tonight. Speed does not merely cost the traveler, it costs the observation. What the crew would actually see through a forward window is one of the more frequently misdescribed phenomena in this subject, and the real version is stranger than the popular one.
The first is aberration.
Motion sweeps apparent positions toward the direction of travel. A star that sits 90 degrees abeam when the ship is at rest appears, at speed, at an angle from the bow whose cosine equals beta. At half of light speed, 60 degrees. At 0.9 degrees Celsius, 25.8 degrees. At 0.99 degrees Celsius, 8.1 degrees. At 0.999 degrees Celsius, 2.6 degrees. That is a severe compression. At 0.99 degrees Celsius, everything that was in the forward half of the sky has been squeezed into a cone 8 degrees across, about the width of your fist held at arm's length. And stars that were genuinely behind the ship are swept forward too. So the cone contains not merely the forward hemisphere, but the overwhelming majority of every star in the sky. The second is Doppler shift, and it varies across that cone. Objects near the exact center are blue-shifted by the full factor. Objects at the edge of the cone are shifted less. Objects directly astern are red-shifted by the inverse factor. The third is relativistic beaming. The intensity of light from a source is boosted by the Doppler factor raised to a power which means forward sources are not merely bluer but dramatically brighter, and rearward sources are not merely redder but dramatically dimmer. Put those together, and the view is this. Directly ahead, a small, intensely bright region containing almost every star in the sky, with colors shifted upward through the spectrum. Visible light pushed into ultraviolet, infrared pushed into visible, so the population of what appears in the window is not the population the crew departed with. Around that, a ring where the shift is smaller and the ordinary sky is compressed and distorted. Behind, near total darkness, because everything that would have been there has been swept forward, and what remains has been redshifted and dimmed below detection. This effect is sometimes called the starbow, a term coined in the 1970s to describe a predicted rainbow-colored ring. Later and more careful calculations found the popular illustration to be wrong in an important way, because the shift moves the entire spectrum rather than selecting a band, and because stars have broad continuous spectra, the result is not a clean colored rainbow. It is a bright forward concentration whose color depends on the intrinsic spectrum of each source and on where it sits in the cone. What is unambiguous is the geometry. The cruise window shows a shrinking bright circle ahead and expanding darkness everywhere else, and the circle shrinks as the ship goes faster. It is difficult to think of a more literal image for what this entire trade costs. The faster you go, the less of the universe you can see, and all of it collapses into the one direction you are already committed to. That compressed view creates a navigation problem that has no analog in any flight regime humans have operated in. Spacecraft navigate by star tracker. A camera images a patch of sky. Software matches the pattern of stars against an onboard catalog, and the vehicle's attitude is determined to arc-second precision. It is one of the most reliable technologies in spaceflight, and it works because the sky is fixed and the catalog is correct. At relativistic speed, the catalog is wrong, not corrupted, not out of date, wrong in the ship's own frame by construction, because aberration has moved every star from its cataloged position. This is correctable in principle. Aberration is a deterministic transformation. Given the ship's velocity, the correct apparent positions can be computed exactly. Star trackers on a relativistic ship would carry the rest frame catalog plus a transformation applied continuously as a function of current speed. The difficulty is that the correction depends on the speed, and the speed is one of the things being measured. There is a circularity. To interpret the star field, you need to know your velocity, and to know your velocity, you need to interpret the star field. It is solvable. An onboard accelerometer integrates proper acceleration and gives velocity independently, but it means the navigation solution now depends on an inertial measurement that has been integrating continuously for years, with drift accumulating the entire time, in a radiation environment that degrades the sensors doing the integrating. There is a second and less tractable problem. Precision degrades where the compression is greatest. At 0.99 key, when the forward hemisphere occupies 8 degrees, the angular separation between two stars that were 30 degrees apart at rest is reduced to a fraction of a degree. Angular measurement precision is fixed by the optics and the detector. So the same instrument that resolved two stars comfortably at rest may not resolve them at all at high gamma, and the geometric dilution of precision, the same effect that makes satellite navigation less accurate when the satellites are clustered, becomes severe. Navigation accuracy falls exactly when navigation matters most. A ship at 0.99 C covers a light year every 12.3 days of Earth time. A pointing error of 1,000th of a degree, sustained over 4.37 light years, produces a miss distance of about 72 astronomical units, well outside the target star's planetary system. One navigation method survives the transition intact, and it is worth noting because it is the exception. Pulsar timing. Certain millisecond pulsars rotate with a regularity rivaling atomic clocks, and their pulse arrival times encode position information that does not depend on angular resolution at all. A ship measuring the arrival phase of several known pulsars can fix its position in 3 dimensions. And because the measurement is temporal rather than angular, aberration compresses the sky without degrading it. The pulses are Doppler shifted, and that shift must be modeled, but the modeling is exact. The technique has already been demonstrated in flight. NASA's Station Explorer for X-ray timing and navigation technology experiment aboard the International Space Station determined its own orbital position from pulsar observations alone in 2017. That is a genuine solution to a genuine relativistic problem, and there are not many of those in this episode. It is also, characteristically, a solution that requires an X-ray telescope pointed away from the direction of travel, which is to say, out of the shield's shadow. And the correction available to fix that error is the subject of the segment after next, where the news is not good. Communication with home degrades in a way that is worth working through carefully, because it is one of the few relativistic penalties that affects the mission even when everything is functioning perfectly. Start with the obvious part. A ship at 4.37 light years cannot have a conversation. A question sent from Earth and answered immediately returns after 8.74 years. Every interstellar mission accepts this, and every deep space mission today already operates under a milder version of it. A command to a spacecraft at Neptune takes about 4 hours each way. The relativistic version adds 3 further penalties. The first is Doppler shift on the link itself. A signal transmitted from Earth to a receding ship arrives redshifted by the inverse Doppler factor. At 0.9 key, that factor is 4.36, so a signal transmitted at 10 gigahertz arrives at 2.3 gigahertz. That is manageable with a tunable receiver, but the shift also stretches the signal in time, which reduces the data rate by the same factor. A link that delivered a megabit per second delivers 230 kilobits. The second is transmitter power and antenna gain. The ship's own transmissions to Earth are blueshifted from Earth's perspective, which helps slightly, but the dominant term is distance. Received power falls as the square of range, so a link that worked at 1 light year needs 100 times the power or 100 times the antenna area at 10 light years. Interstellar communication is not a scaled-up version of deep space communication. It is a different problem with a different answer, generally involving optical rather than radio links and receiving apertures measured in tens of meters. The third penalty is the one that has no engineering answer. The ship's clock is running slow. A crew that experiences 1 year while Earth experiences 11 is receiving 11 years of transmitted material in 1 year of listening time, if the link can carry it, or is falling 10 years behind if it cannot. Meanwhile, every message the crew sends arrives at Earth spread across 11 years. The relationship is not symmetric, and it is not a conversation. It is 2 parties writing to each other at incompatible rates across a gap that widens faster than either can send. And here's the thing that is rarely said directly about this. The crew is not merely out of contact. The crew is out of relevance. By the time a question they ask is answered, the institution that answers it is not the institution they asked. The technology described in the answer has been superseded, and the answer itself was composed by people who have had a decade to change their minds about what the mission is for. Course correction is where several of tonight's threads converge, and the result is a genuine trap. A ship at cruise needs to steer for ordinary reasons. Navigation errors accumulate. The target's proper motion must be tracked. Any deviation introduced by an impact, an uneven thrust, or a mismodeled density gradient must be corrected. Every real mission budgets a velocity change, allowance for this, a delta V reserve, and on conventional missions, it is a small fraction of the total. At relativistic speed, steering costs are calculated in rapidity, not velocity, and this changes the picture completely. A lateral velocity change of 1 kilometer per second is, at rest, an unremarkable maneuver. Applied to a ship traveling at 0.9 K, the same lateral change produces an angular deflection of only about 0.0002 degrees, because the forward velocity is 270,000 kilometers per second, and the lateral increment is 1. Turning a relativistic ship is not like turning a slow one. It is like trying to change the direction of a bullet by breathing on it. To produce a useful course change, say a tenth of a degree, enough to correct a significant targeting error across light years, the ship at 0.9 C needs a lateral velocity change of about 470 kilometers per second. That is more delta V than the entire Apollo program expended, applied sideways, in mid-cruise, using propellant that has been carried at the full mass ratio penalty since departure. Now add the constraints we established earlier. The ship's radiation protection is a forward shield, and the crew survives only within its geometric shadow. Applying lateral thrust requires either a thruster mounted outside the shadow, exposed to the beam, or turning the vehicle, which exposes the flank. So the maneuver that corrects the navigation error requires either putting hardware into the beam or putting the crew into it. There is a version of this that works, and it is the same answer as everywhere else in this episode. Correct early and correct slowly. A small angular change applied at the beginning of the cruise, when the ship is still accelerating and the engine is running anyway, costs almost nothing. The same change applied at the end costs everything. Which means the navigation solution must be right at departure, based on a stellar position measurement made before the voyage, extrapolated forward through decades of proper motion, aimed at a star that will have moved measurably by the time the ship arrives. Alpha Centauri's proper motion is about 3.7 arc seconds per year, which across 40 years is 148 arc seconds. A real angle, easily accounted for, but only if the model of its motion is correct and remains correct. The ship is committed at departure in a way that no previous vehicle has ever been committed. And then there is the divergence, which is the cost that no amount of engineering touches. Return to the 1G voyage. 3 years of ship time buys 9.78 light years of distance and gamma of 11.1 and costs 10.7 years on Earth. 5 years of ship time buys 83.6 light years and costs 84.6 years on Earth. Those Earthside numbers are not an inconvenience. They are the mission's actual duration as experienced by everyone who is not aboard. A crew that departs on a 5-ship-year voyage and returns by the same profile has been gone 10 years by their own reckoning, and roughly 170 years by the reckoning of the world they left. Every person who planned the mission is dead. The agency that funded it may not exist. The language has drifted. The scientific questions the mission was designed to answer were answered by other means, decades ago, by instruments that were not invented at launch. There is a specific version of this problem that mission designers call the weight calculation, and it is uncomfortable in a way that is easy to underestimate. If a ship departs for a star 40 light years away at a speed that takes it 100 Earth years to arrive, and technology continues to improve, then a ship launched 50 years later at a higher speed may arrive first. The first mission is overtaken by its own successor in flight, unable to do anything about it. That is not a hypothetical inefficiency. It is a genuine argument made seriously in the interstellar literature that there exists a wrong time to launch, that departing too early wastes the crew and the ship on a journey a later vessel would perform better, and that the rational moment to go is later than enthusiasm suggests. For a crew, the divergence has a more immediate shape. Their clock is the slow one, which means the universe is what ages. Every message from home is old on arrival and older on reading. The people they knew are not merely far away, they are in the past, moving into the past faster than the ship moves through space, at a rate the crew chose and cannot now reduce. And unlike every other cost in this episode, this one does not respond to engineering. There is no shield for it. There is no material with a higher tolerance for it. There is no design margin that reduces it, because it is not a failure mode. It is the mechanism working exactly as intended. The time dilation that makes the voyage survivable is the same time dilation that removes the crew from the civilization they are traveling on behalf of. The gift and the penalty are the same effect, viewed from two sides. We said that at the beginning of the night. This is where it costs the most. Science is the reason to go, and relativistic speed interferes with the science in ways that are rarely counted against it. Consider the corridor itself. A ship crossing 4 light years of interstellar medium is passing through a volume no instrument has ever sampled, containing exactly the material that determines whether the next mission is possible. It is, in principle, the most valuable measurement opportunity of the entire voyage, a continuous transect of the medium between two stars. At relativistic speed, most of that measurement is unavailable. A dust detector works by allowing a grain to strike a sensor and measuring the resulting charge or crater. At a fifth of light speed, the grain does not strike the sensor. It passes through the sensor and through the structure behind it, having deposited a fraction of its energy in a region far smaller than the detector's resolution. The instrument records an event without characterizing it. A gas spectrometer works by capturing atoms and analyzing them. At relativistic speed, there is no capture. Every atom arrives with energies in the hundreds of millions of electron volts, which is not a sample. It is a bombardment, and the instrument required to characterize it is a particle physics detector rather than a spectrometer. Heavy, power-hungry, and itself degraded by what it is measuring. Optical astronomy is compromised in a different way. Aberration and Doppler shift mean the telescope is not looking at the sky in its rest frame. Everything can be transformed back mathematically, and the transformation is exact, but the instrument sensitivity is not uniform across wavelength. A telescope designed to observe visible light finds visible light shifted out of its band ahead and into its band from unexpected sources. The observation is possible. It is simply not the observation the instrument was built for, and the destination encounter in a flyby profile, lasts hours. A ship crossing the Alpha Centauri system at 2/10 of light speed traverses the distance from the star to a planet at 1 astronomical unit in about 41 minutes. The entire region of interest, out to, say, 30 astronomical units, is crossed in under 21 hours. Compare that with what a slow arrival buys. Cassini spent 13 years in the Saturn system. Juno has been at Jupiter since 2016. New Horizons, which did fly past at speed, returned extraordinary data from Pluto and then spent 16 months downlinking it, having gathered it all in a window of a few hours. So the mission profile that gets there soonest is also the profile that learns least on arrival and learns least along the way. There is a real sense in which relativistic speed optimizes for the one quantity, elapsed crew time. That is not what the mission is for. Slower ships are worse at traveling and better at everything traveling is supposed to enable. Arrival introduces a hazard that the cruise phase does not, and it follows from a fact so simple it is easy to overlook. A star system is full of material, and the ship is still moving at cruise speed when it gets there. The interstellar medium at 1/10 of an atom per cubic centimeter is the emptiest environment the ship will encounter. A planetary system is not that. It contains dust produced continuously by collisions between asteroids and by the sublimation of comets, and the density of that dust exceeds the interstellar background by orders of magnitude. In our own solar system, the zodiacal cloud, the diffused disk of dust responsible for the faint glow visible from a dark site before dawn, has a number density near Earth's orbit that is roughly 1,000,000 times the interstellar dust density for comparable grain sizes. It is the reason the inner solar system glows in infrared, and the reason every spacecraft that has flown through it carries measurable micrometeoroid damage. Now fly through that at 2/10 of light speed. Every impact energy computed earlier scales directly with the number of impacts, and the number of impact scales with density. A ship that would suffer a serious grain strike once per interstellar crossing suffers the equivalent exposure within a small fraction of a single astronomical unit inside a dusty system. There is an additional and specific concern for the destination we most want to visit. Alpha Centauri is not a single star. It is a triple system. Two sun-like stars, A and B, orbiting each other on an eccentric 80-year orbit that brings them between about 11 and 36 astronomical units apart, plus the distant red dwarf Proxima. Dynamical modeling of such systems generally predict that the gravitational stirring from the companion star raises collision velocities in any debris disk, which grinds material more efficiently and can sustain a dustier environment than a single star would. The observational picture is more encouraging than the theory. Infrared searches have not detected a bright excess around Alpha Centauri A or B, which places genuine limits on how much warm dust can be there. That is reassuring, and it should be stated as such. But absence of a detected excess is a limit, not a measurement. And the limit sits well above the density that would matter to a hull arriving at 1/5 of light speed. An environment can be far too faint to detect from 4 light years away and still be crowded from the point of view of something crossing it at 60,000 kilometers per second, which produces an awkward inversion. The safest part of the voyage is the empty part in the middle. The dangerous part is the destination, the only part the mission actually wanted. There is a category of cost that no equation in this episode captures, and it belongs in an honest account. A relativistic mission is irreversible in a way that no human expedition has ever been. Every previous voyage of exploration, however dangerous, retains some form of the option to turn back. Ships have returned from the Antarctic with the mission abandoned. Apollo 13 came home. The International Space Station has always had a return vehicle docked to it, and the reason is not sentiment. It is that a crewed vehicle without an abort path is a different kind of object. A ship at 0.2 of light speed, 1 light year out, cannot turn back. Not in the sense that turning back would be difficult, in the sense that reversing the velocity costs the same mass ratio that produced it, squared, and that propellant was not carried, because carrying it would have prevented departure. The consequences of that are worth stating precisely rather than dramatically. There is no resupply. Every consumable required for the mission, every gram of food, every filter, every spare, every gasket must be aboard at departure or manufacturable en route from material also aboard at departure. Closed-loop life support at a scale and reliability far beyond anything demonstrated becomes not a convenience, but a precondition. Biosphere 2 taught us how hard sealed ecology is at 2-year scale with a repair crew outside. This is decades, sealed, with no outside. There is no rescue. The nearest possible assistance is at the origin, receding at cruise speed, and any vessel dispatched to help would need to match the first ship's velocity, which is the full mission cost again, arriving years after the emergency. There is no repair from outside. Damage from a grain impact, a shield failure, a reactor fault must be handled with what the ship carries and what the crew can do in a radiation environment that is itself degrading the electronics they would use to diagnose it. And there is no reconsideration. A crew that decides 3 years in that the mission's premise was wrong has no mechanism for acting on that conclusion. Every decision of consequence was made before launch by people the crew may never speak with again in any meaningful sense. Set that beside the radiation and the dust and the mass ratios, and a pattern emerges that is really the argument of this whole episode. Each individual problem has a partial engineering answer. Shields help. Magnetic deflection helps. Sacrificial ice helps. Graphite is better than quartz. Spin helps. Sloped noses help. What none of them touch is that every one of those answers is a one-time bet placed at departure on a vehicle that cannot be adjusted for a journey whose environment we have never measured. So, what does slower actually buy? This is where the arithmetic finally produces something constructive, because almost every penalty tonight has been a function of gamma, and gamma is the one parameter a designer controls. Start with the historical designs, because they encode this reasoning already. Project Daedalus, studied by the British Interplanetary Society between 1973 and 1978, remains the most complete interstellar vehicle design ever produced. It targeted Barnard's star, about 6 light-years away. Its cruise speed was approximately 0.12 degrees Celsius, a little over 1/10 of light speed. Its departure mass was about 54,000 tons, the overwhelming majority of that being helium-3 and deuterium fuel for a two-stage inertial confinement fusion drive. It carried no braking stage and would have performed a flyby. Project Longshot, developed at the U.S. Naval Academy with NASA between 1987 and 1988, took a different position. It targeted Alpha Centauri, and it insisted on orbital insertion. It wanted to arrive and stay. To afford the braking, it cruised at about 0.0455, roughly a third of Daedalus's speed. Its transit time was about a century. Look at what the slower design bought. At 0.0455, gamma is 1.001. Proton arrival energy is about 0.95 million electron volts, a factor of 5 below Daedalus's cruise and a factor of 150 below a 0.55 ship. Dust impact energies fall by the same factor. Radiation dose falls faster still because the flux term falls with speed as well. Waste heat at the bow drops by more than an order of magnitude. And because the mass ratio is exponential in rapidity, the propellant requirement for the entire mission, including braking, became small enough that a fusion pulse drive could carry it. Longshot bought orbital insertion, a survivable radiation environment, a manageable dust environment, and a design that closes. It paid with 100-year transit and the acceptance that no member of the launch team would see the data. That is the trade in its clearest form. And the arithmetic tonight points consistently toward the same conclusion. For a mission carrying anything fragile, the optimum cruise speed is probably low, somewhere in the range where gamma remains near 1, and every hazard stays linear rather than divergent. This should be stated as a conclusion the numbers point toward rather than a settled result, because it depends on assumptions about shielding technology and about the medium that could change. But the direction of the argument is robust. Every mitigation in this episode works better slowly. Every hazard grows faster than speed. The two curves cross, and they cross well below the speeds that popular imagination reaches for. The fastest interstellar mission is not the best interstellar mission. It may not even be the one that arrives. There is a version of this conclusion that sounds like defeat, and it is worth taking apart because it is not what the numbers say. The numbers do not say interstellar travel is impossible. They say something more specific and more useful. That the difficulty is not distributed the way intuition places it. Intuition places the difficulty in propulsion. Build a better engine and the stars open. The arithmetic says propulsion is roughly the third hardest problem, behind the medium and behind irreversibility, and that solving propulsion in isolation makes the other two worse, because a better engine is an invitation to go faster. Intuition places the reward in speed. The arithmetic says that above a certain cruise velocity, additional speed purchases crew time, which is genuinely valuable, at the cost of radiation dose, erosion, thermal load, impact energy, navigation precision, communication bandwidth, and mission science, all of which degrade faster than the crew time improves. Intuition treats interstellar space as empty. The arithmetic says it is empty at 1/10 of an atom per cubic centimeter, and that this is genuinely, extraordinarily empty, and that emptiness is not a property of the medium alone, but of the relationship between the medium and your speed. The same volume that is a perfect vacuum to Voyager is a particle accelerator to a ship at half of the light speed. Nothing about the hydrogen changed. And there's a genuinely hopeful reading available here, which the arithmetic supports rather than merely permits. If the optimum speed is low, then the hardest requirement is not an exotic drive. It is patience, closed-loop life support, and materials that last. Those are difficult, but they are difficult in the ordinary way. The way that responds to incremental engineering, to iteration, to testing in the solar system, where failures are recoverable. A closed ecology that runs for a century can be developed in orbit. A fusion pulse drive at 0.05 key is a substantially easier target than one at 0.5 key. A hull that survives a low gamma medium is a hull we could specify today. The stars are not behind a wall that requires new physics. They are behind a set of engineering problems that get easier the less we hurry. That is a different kind of statement from the one usually made about interstellar travel, and it deserves to be made plainly because it changes what a serious program would actually build first. We have talked about a great deal tonight, and it is worth assembling it before we finish. We have talked about the ladder of speeds and where along it the medium stops behaving like emptiness. Somewhere near a tenth of light speed, where a ship covers 30,000 kilometers every second and reaches Alpha Centauri at 4.37 light years in a little under 44 years. We have talked about the one genuine gift and its exact shape, time dilation, which compresses the cruise clock and the corridor ahead of them, and compresses neither the energy bill nor the Earthside calendar. We have talked about the rocket equation and rapidity, and about mass ratios of 58 to reach a fifth of light speed, of 59,000 to reach half of it, and about what happens when the mission decides to stop and the exponent doubles. We have talked about the interstellar medium at roughly a tenth of a hydrogen atom per cubic centimeter, 120 atoms in a volume the size of a milk carton, and about how velocity converts that into trillions of particles per square meter per second, each carrying the energy of a therapeutic beam. We have talked about Semyonov's estimate of 60 rem per second at a tenth of light speed against an annual safe limit of 10, and about the shield that stops the beam and then generates neutrons and muons inside itself. We have talked about waste heat and radiator area and the fourth power of temperature, about dust and the steep size distribution, and the 100 micrometer grain that arrives carrying the energy of 3.7 kilograms of TNT. About Hoang and colleagues' 0.5 millimeter eroded from the bow on the way to Alpha Centauri. About Whipple shields that need a 2-kilometer standoff and starbows that shrink the visible universe to a cone 8 degrees across. And we have talked about the divergence, the Earth-side decades that accumulate while the cruise clock runs slow, which is the only cost tonight that no material and no design margin touches. So here's the answer to the question we started with. Is traveling near light speed worse than you think? It is, but not because it fails. It is worse than you think because it works. Because relativity delivers exactly what it promises, compresses the crew's journey precisely as advertised, and charges the entire difference to everything else in the system. The shortened voyage is real, the bill is real, and the bill arrives in currencies the traveler cannot pay from the traveler's own account. Energy, mass, dose, erosion, elapsed centuries at home. There is a way of holding all of this that makes it less like an obstacle and more like a description. Everything we have discussed tonight is, at bottom, a single physical fact seen from many angles. The universe does not contain a special substance that resists fast travel. There is no ether, no barrier, no field that pushes back on ambition. There is only ordinary hydrogen, ordinary dust, ordinary starlight, and ordinary background radiation, the same materials that have been sitting quietly between the stars for billions of years, doing nothing at all. What changes is the relationship. Everything in this episode is a consequence of your speed relative to something that was already there. Then it first appears, and it does not stay in space. You are, at this moment, moving through the same kind of arrangement. The Earth is traveling around the Sun at about 30 kilometers per second. The Sun is carrying the whole solar system around the galactic center at roughly 230 kilometers per second. And the local interstellar cloud, the wisp of warm hydrogen we happen to be inside, is moving past us at about 26 kilometers per second, which means interstellar hydrogen is streaming through the solar system continuously and has been for the whole of recorded history and will continue for tens of thousands of years more. It passes through the outer solar system, through the region where the Voyagers are, through the space between the planets, and a small fraction of it reaches us. It is not dangerous. It is not even detectable without an instrument built specifically to find it. The medium extends us the courtesy of behaving like emptiness, and it extends that courtesy for one reason only. We are slow. Everything that makes deep space survivable for us, the mildness of the medium, the harmlessness of the dust, the coolness of the background sky, the fact that our clocks and everyone else's agree, is not a property of the universe being gentle. It is a property of us not being in a hurry. We are sitting inside a particle accelerator that has been switched off by our own velocity, and the switch has no other setting available to us. There is a version of this that applies well beyond spacecraft, and it is worth carrying out of tonight. Most of the things that surround you are neutral at the pace you are living. They become something else only when you decide to move through them faster than they were meant to be moved through. The hydrogen does not change. The relationship does. The space between the stars holds roughly 1/10 of a hydrogen atom in every cubic centimeter, not 1/10 of a gram. 1/10 of a single atom averaged across a volume about the size of a sugar cube. It is the emptiest volume any human instrument has ever measured, and it will still be the emptiest volume in the universe on the day someone finally builds a ship that has to fight it. It has not changed in 4 billion years. It will not change for the ship. 1/10 of an atom, harmless at walking pace, harmless at 11 kilometers per second, harmless for the whole of human history and for the whole future in which nobody hurries. Then a threshold and a beam and a bill. The stars are not far because the universe is hostile. They are far, and the universe is indifferent. And indifference turns out to be a harder thing to engineer around than hostility would have been. Somewhere above us tonight, the Voyagers are still moving outward at 17 kilometers per second, which is 0.000057 of the speed of light, through a medium that does not notice them, and will not notice them for the 40,000 years it takes them to approach another star. They're the slowest possible answer to the question we asked tonight. They are also the only answer that has ever actually left. Good night.